So now we're going to look at a very useful theorem called the initial value theorem. So I'll describe it in words here, but it's a bit of a mouthful and it's difficult to understand in words. But you'll really get an understanding of it whenever we work through the final example here. So the initial value theorem tells us that we can find the initial value in the time domain of a function by looking at how the complex frequency domain of the function behaves at infinity. So if we were to take the Laplace transform of some function g of t, we would get a function g of s. So we can say that g of s is equal to the integral from 0 to infinity of g of t e to minus st by dt. Now what we're going to do is we're going to take that very same Laplace transform and we're going to look at the limit as s tends to infinity. Now we know that as s tends to infinity, then that e to the minus st is going to tend to e to the minus infinity. So this whole thing is going to dominate and it's going to tend towards 0. So that whole limit there will tend towards 0. So equally, if we were to look at the limit as s tends to infinity of the Laplace transform of a derivative, then we've seen that the Laplace transform of a derivative from the previous video is going to equal s times f of s minus f of 0. But we know from this here that this whole thing is going to equal 0 because as s tends to infinity, this term dominates and the whole thing tends towards 0. So we can say that the limit as s tends to infinity over s times f of s minus f of 0 must equal 0. So the identity we're looking for is, if we take the f of 0 over to the other side here, we'll go f of 0 equals the limit as s tends to infinity of s times f of s. So that's really telling us that we can find the initial value of a function in the time domain by taking the Laplace transform of the function, multiplying it by the value of s, and letting s tend towards infinity. So it really means that we can figure out what the initial value of a function in the time domain is simply by looking at it and messing about with it in this format in the frequency domain. So that's really what we've got written here. We can find the initial value of a function in the time domain without doing the inverse transform, so we do everything in the frequency domain. So here's an example here. Let's imagine we had the complex function f of s equals 1 upon s minus a for a greater than 0. Then our contention then up here from this little identity is that we can find the f of 0 by taking the limit as s tends to 0 of s times our function f of s. So it's going to be s upon s minus a. So we just multiplied this function here by s. Now as that limit as s tends to infinity of this here is going to equal 1. So that's telling us that we can find the value of the function, the initial value of the function in the time domain, and the initial value of the function in the time domain is just going to be a value of 1. So let's check and see if that is the case. If we were to find the inverse transform of this here, that would be f of t equals e to the at u of t. And we're looking for the initial value, so when we put in the value for when t equals 0, well when t equals 0 here, we're going to have e to the power of 0, and the power of 0 is just 1. So 1 times u of t is just going to be a value of 1. So indeed that f of t does give us a value of 1, just as we've seen here. So we were able to find that initial value in the time domain without having to go back into the time domain here, without having to do the inverse transform. We can find that initial value by staying in the complex frequency domain, multiplying by s and taking the limit as s tends to infinity. So that's all there is for this video. I'll get you on the next video. Goodbye.